All right, polar molecules. So we know that we can classify bonds as polar or nonpolar. We can also classify molecules as polar or nonpolar molecules, but there's more at play here than just the two atoms in a bond. So what are the determining factors as to whether a molecule overall is polar or not? Okay, so this is more big picture, where we've talked about individual bonds. We know molecules are made up of individual bonds, so there's more things we're going to have to consider. One is we have to see, are there any polar bonds in our molecule? Okay, that's definitely something to consider. Do we have any lone pairs? Because guess what? A lone pair is electrons, and that is a concentrated area of negative charge, okay? A concentrated area of negative charge. And it's the uneven distribution of negative charge that makes things polar or nonpolar. So that's why lone pairs are also important to consider here. The last thing we have to consider is the shape of the molecule. Okay, so these three things, if you have a question on the exam, which molecule is polar, which molecule is not polar, whatever, you need to know these three things. This is going to tell you whether a molecule is polar or not, or at least know how to judge these three things. So let's look at water, for example. Water, H2O, we have the oxygen, we have two lone pairs on that oxygen, we have hydrogens, all right? So you have to know how to draw Lewis structures, number one, to gauge if something is a molecule will be polar or not polar. You have to be able to visualize how things are pieced together. So if you're not well versed in Lewis structures, you're not going to be well versed in determining the polarity of a bond or a molecule. So let's consider, do we have any polar bonds in our molecule? Well, hydrogen, let's look at the electronegativity chart right up here. Hydrogen has an electronegativity value of 2.1 and oxygen has a value of 3.5. So let's calculate the difference. 3.5 for oxygen minus 2.1, that was hydrogen, and we get a difference of 1.4. This is definitely polar, right? Above 0.5 and less than 1.9 is a polar bond. So both of these bonds are polar, and in fact we've drawn in the partial positive signs on hydrogen because they are the less electronegative element. They're the electron poor portion of the molecule. So we have two polar bonds, so yes, check. We also have lone pairs, and instead of putting the partial negative sign on the oxygen, we just go ahead and put them on the lone pairs because we know that's where the negative charge is. Okay, we know that's where the electrons are. And if that's the case, if you can draw in one portion of the molecule as partial positive, another portion of the molecule as partial negative, then what you can also do is draw in this little symbol here. So I'm going to put a box around this symbol. What is this? This is an arrow with a plus sign at the opposite end. We call this a dipole. Okay? A dipole is an indication or an indicator of a polar molecule. If you can draw a dipole on a molecule, then that molecule is polar. Now, there will be one exception that we'll talk about on the next slide. But we have a dipole. A dipole always points towards the negative region of the molecule. Okay, it points towards these partial negative signs. So you draw the arrow pointing towards the partial negative, and then if you put a little cross on the arrow at the opposite end, it looks like a plus sign. Right? So that plus sign is indicating which region of the molecule is partial positive. So the plus sign on the arrow is closer to the partial positive, the electron deficient portion of the molecule, and the arrow is pointing towards the electron rich portion of the molecule. So overall, water is a polar molecule because there is an uneven distribution of negative charge and electron location. We've got polar bonds, we've got lone pairs. Now, we'll talk more about the shape of a molecule in a minute, but this is a polar molecule. Another good example is what we call chloromethane, CH3Cl. Chlorine is a halogen. It's right next to fluorine. And remember, however close an element is to fluorine determines how electronegative it is. Fluorine is the most electronegative element on the periodic table. Chlorine has a value of 3.0. So again, let's just walk through this step by step. Does this molecule have polar bonds? Well, let's look at carbon and chlorine. We've got a bond there. The carbon-chlorine bond, I am going to zoom in down here. Wait, first, carbon has a value of 2.5. So 3.0 and 2.5. So we've got two kinds of bonds. One bond is right here, carbon and chlorine. We're going to look at, is this bond polar or not? Carbon to chlorine. Well, carbon we said was, well, I'll do the highest one first, sorry. Chlorine was 3.0, minus carbon was 2.5. 3.0 minus 2.5, that's a difference of 0.5. That is polar. So yes, this is polar. And now we also have another kind of bond. We have carbon-hydrogen bond. We've got three of them, actually. Carbon-hydrogen. Is this polar? Carbon is 2.5. Hydrogen is 2.1 if you look at the table. So this is a difference 0.4. This one is not polar. Okay, so I'm going to put an X, not polar. So here's the deal, though. We do have a polar bond in our molecule. So let me erase. I'm going to zoom in. This bond right here is polar. These bonds, okay, these are non-polar. All right, but again, overall, we do have a polar bond in our molecule. Now, do we have any lone pairs? And they're not drawn in, but yes, we do. On this chlorine atom, we have 3 lone pairs. So this is a very electron-rich part of the molecule. Why? We have 3 lone pairs, and it's involved in a polar bond. So we're going to put the partial negative sign on chlorine, and the opposite end of the molecule, these hydrogens, are the electron deficient portion. These are the partial positives. So we put a partial positive on literally every hydrogen. Now, when you have uneven distribution of electrons like this, what do? We can draw in a dipole, indicating that yes, this is a polar molecule. Okay, it's pointing towards the electronegative side of the molecule, the chlorine. And that plus sign is on the partial positive region of the molecule. Okay, these rainbow colored pictures, the red regions indicate a lot of electron density, and the blue regions indicate a lower electron density or electron deficiency, I should say. And that just helps you visualize molecular polarity, I should say. Okay. If I'm talking fast, if I'm moving quickly, just pause the video, slow it down, rewatch it as you need to. I just didn't want to make these 20-minute videos each. So let's look at some more examples. The last thing we said is we also need to consider the shape of a molecule. We haven't really talked about that yet. If there is symmetry in your molecule, you may have dipoles, you may have polar bonds, you may have lone pairs. But if there is symmetry in the molecule and your dipoles are pointing in opposite directions, then what happens is they can cancel each other out. So I'm reading right down here. If symmetry exists, overall, there is no net polarity within the molecule. Because the dipoles, what happens, I'll show you in a second, they will cancel each other out. So let's look at carbon dioxide as a classic example. The carbon-oxygen bond is polar. We actually looked at that when we talked in the video about polar bonds. I think, what's the value for oxygen? 3.5 and 2.5. So 3.5, this is the value for oxygen, minus 2.5, that was the value for carbon. That equals a difference, electronegativity difference of 1. So this is definitely polar. All right, so these bonds down here, these are polar bonds. Now, because of that, we put the partial positive on carbon, and you can see we put the partial negative signs on oxygen. Now, let's go ahead and draw in our dipoles. Remember, you draw dipoles in pointing towards the partial negative sign, so we're actually going to have to draw 2 dipoles here. One pointing this way, and one pointing the other way, towards those partial negatives. Now, because there's symmetry in this molecule, I'm going to draw my plane of symmetry right down, smack dab down the middle of the molecule. Because there's symmetry here, notice that these dipoles cancel each other out. If they're pointing in opposite directions, then there's no net polarity overall. They cancel one another out. Okay? So 0 net polarity. This is a non-polar molecule. So you can have lone pairs, and in fact these oxygens also have lone pairs. Those are not drawn in. You can have lone pairs, you can have polar bonds, but if the shape of the molecule is such that it is symmetrical, It is a nonpolar molecule. Another example is carbon tetrachloride, carbon with 4 chlorines. All of these carbon-chlorine bonds, look, we calculated this on the slide above, a difference of 0.5. So these are all polar bonds. This molecule has only polar, it's full of polar bonds. And we have lone pairs all over these chlorines, all right? So we put a partial negative on all the chlorines. The carbon is the electron deficient atom in the molecule, it's partial positive. So if I were to draw a dipole in, I would point it towards one going up. It might help if I draw the Lewis structure for this. I want to draw the Lewis structure really quick to illustrate a point. If you are drawing the Lewis structure for a carbon with fluorochlorines, you're going to draw a structure that looks like this. It's harder to visualize this in 3D. Okay, so here's our Lewis structure. We have a molecule north and south, a molecule east and west. Let me draw in my partial positive and partial negative. So carbon is my partial positive and chlorine is the partial negative sides. So I'm going to draw a dipole pointing towards every partial negative. So I'm going to draw one pointing from carbon towards the chlorine on the right and from carbon pointing towards the chlorine on the left. I'm going to draw one pointing from carbon towards the chlorine up and from carbon pointing towards the chlorine down. So what do we notice? Because there is symmetry in this molecule, the dipole pointing east and west, they cancel each other out. The dipole pointing north and south, they cancel each other out. So again, there is zero net polarity because there's symmetry. And it's harder to visualize it in this molecule here. That's representing the molecule in 3 dimensions. It's easier if you look at the Lewis structure because you have dipoles pointing opposite directions. Okay. All right. Let's do some more practice. I would like for you to draw in, okay, right here, draw in the dipoles and the partial positive negative signs on these molecules. Look at if there's symmetry or not. So let's consider this first one, hydrogen cyanide. We have a carbon, a hydrogen, and a nitrogen. So first off, do we have a partial? Can we assign a partial positive, partial negative region of the molecule? Do we have or polar bonds, in other words? Well, let's look at the electronegativity chart. Carbon has a value of 2.5, nitrogen 3.0, hydrogen 2.1. So I'm going to draw those, I'm going to write those numbers in, 2.1, 2.5, 3.0. So the difference for these bonds right here is 0.5. That is polar. So we have a polar bond here. The difference between 2.1 and 2.5 is 0.4. So the carbon-hydrogen bond is not polar, never polar. So we have polar bonds. We have a lone pair here, so this is definitely going to be the partial negative side. We have the more electronegative element nitrogen, and we have a lone pair. This is the partial negative side, which makes the opposite end of the molecule partial positive. That's hydrogen. Now, do we have symmetry? No, we don't. So if we draw a dipole in, we should draw it from the partial positive side pointing towards the partial negative side. So this is definitely a polar molecule. There's our dipole. All right, let's look at C2H3Cl, this molecule down here on the left. Carbon chlorine, we calculated that earlier. Where is it? Right here. Carbon chlorine had a difference of 0.5. That's a polar bond. And remember, we just said the carbon-hydrogen bond is never polar. So we have one polar bond here. We have lots of lone pairs on that chlorine. So that is definitely our partial negative portion of the molecule. There's a lot of electron density there. And the hydrogens are therefore the electron poor. Oh, this should be pluses. So can we draw a dipole on this molecule? Yes, we can. There's no symmetry. And what I'm going to do, I'm just going to draw it in general kind of over the body of the molecule. This is Totally valid. Okay? From the partial positive regions, in general, you just want to draw one dipole. You don't need to draw like, I know there's been times where we drew multiple dipoles up here when there's symmetry to show how they cancel. But if you have a polar molecule, in general, you just draw one main dipole. Okay, let's look at methyl lithium over here. We have a lithium atom, carbon, and hydrogen. Well, we know the carbon-hydrogen bonds are not polar, but what about carbon and lithium? Where is lithium? It's group 1, main group 1. Here it is right here, a value of 1.0. Carbon is 2.5. Let's write these in. 1.0. Carbon was 2.5. So, the difference there is 1.5. This is definitely a polar bond. But here, carbon is the electron-rich part. Okay, so I got to draw my partial negative. Carbon is partial negative. Lithium is partial positive. Remember, the carbon-hydrogen bonds are not polar, so we cannot put a partial positive, partial negative on the hydrogens, okay? So because of that, can we draw a dipole? Yes, we can. Pointing down towards, from the lithium towards the carbon. All right. This was going to be another poll if we were doing it in our live lectures, but I want you to walk through this problem. Which of the following molecules is not polar? Okay. So you need to draw the Lewis structures. Consider, do I have polar bonds? Do I have any lone pairs? Put in my partial positive, partial negative signs. And then can I draw a dipole? Is there symmetry? That's another thing you ask. So let's look at NH3. The Lewis structure looks like this. And then we have a lone pair on nitrogen. So let's go find the electronegativity values. Nitrogen is 3.0, hydrogen is 2.1. So nitrogen, we got 3.0 minus 2.1. That's a difference of 0.9. This is totally full of polar bonds. So we're going to draw in our partial negative on nitrogen, and plus it has a lone pair. We're going to draw in the partial positives on these hydrogens. All right, now let's draw a dipole. We don't have symmetry, so we draw a dipole. I'm going to draw it just from this end pointing towards that lone pair. Okay, you can draw it on top of the molecule if you want. You can draw it to the side of the molecule. Just indicating that we do have a direction of net polarity towards that partial negative region, towards the lone pair. Okay, let's talk about water. We actually already looked at water, very first slide of this video, but let's draw a molecule of water. So we have hydrogen, oxygen. We know this molecule is bent. We've got two lone pairs on oxygen. You can draw them just as the dots, or you can put little clouds around them if you want. Hydrogen has electronegativity value of 2.1. What is it for oxygen? Oxygen is 3.5. So let's go back down here. 3.5 minus 2.1 is 1.4. So these are definitely polar bonds. Oxygen hydrogen bonds are polar, so we're going to put our partial positive sign on the hydrogens because they are electron poor. All those electrons are being hogged towards oxygen. And this is the electron rich side. All those lone pairs, the electronegative oxygen atom. So let's draw the dipole in. We would draw it from the hydrogens towards the lone pairs. So far, both of these are polar. Ammonia, NH3, and water. What about CH3Cl? I think did we have an example? Yes, up here, we looked at CH3Cl. Boom, it has a dipole. We talked about it, so it's definitely polar. So, yep, polar. What about CO2? Well, this was actually an example right here. Here is CO2, and we said there's symmetry there. We walked through this, so therefore there's zero net polarity, so this is nonpolar.